The last technique we're going to work on in integration is inverse trig functions. The patterns are the same as the ones you know from differentiation, only this time instead of going from the arc sine to its derivative, we're going to be working on its derivative going back to the arc sine. So this is what we have to do, is recognize these patterns in reverse. So let's go right ahead and try an example. The first one, when you look at it, hopefully you can see that this is connected to the arc sine pattern. Now, these are handy ways to remember the derivatives here in terms of u and a constant and u is a function. So our job is going to be to try to be able to say what these values are. So in this problem, it's nice, u is just the value of x. And if I look again here at 4, that tells me that the value of a is 2 because it's a squared. And that's the case in all of these here. You'll see that u becomes squared and a becomes squared when you look in any of these in the patterns. So let's keep going on this example. If I was then to apply the pattern up to here, I would end up with the arc sine of x over 2. In the second example, we can't quite go right away because there's no inverse trig function that corresponds with x plus 2. Instead, what we're going to do is split this fraction into two pieces. That's a technique we've been talking about now in our course, and hopefully you're starting to recognize that. One thing you can do is split this up. When you have a monomial denominator, it's a good thing to try when you get stuck, splitting your fraction up to make it less complicated. So if I look at these pieces here, remember we have a whole host of techniques that we've been practicing for integration. We have to ask ourselves which ones we're going to use. And usually the first thing you want to ask yourself is, can I just use substitution? Because that's probably our most versatile technique. And that's the case here. If I was to take a look at this piece, the derivative here is going to be negative 2x. So when I'm thinking ahead, all I'm missing is this constant. So yeah, it can work with substitution in this example. So what I'm going to do is let u be equal to 4 minus x squared, and du is going to be negative 2x dx. So I've already gone and balanced out my integral. I put the negative 2 in front here, and then I balanced it out by putting a negative half in the front. So that'll be enough to get us started on this piece. So let's just put the first piece down. And this is the integral for, now it becomes du over root u. For the second piece, this again, if you think of your patterns here, I can't see a function in the derivative, so I know I'm not going to be able to use excuse me, I know I'm not going to be able to use substitution or natural log or any of the other ones that we've talked about. So usually it's going to boil down to one of these then. So if I looked here, I would match up the pattern, and there it is again, arc sine, just like we had before. The only difference now is I've multiplied by 2, which is just multiplying by a constant. So I can go ahead and label this as u is x in this case, and a is 2. So I can resolve that integral right now. It's 2 times the arc sine of x over 2 plus some constant. Now, I still have to resolve the first integral I was dealing with, and it'll probably be easier if we rewrite this using the exponent. So that way it'll be easy to apply the power rule in reverse. So the power rule in reverse here, that'll be negative 1/2. So I add 1, and I'll divide by the exponent, plus 2 arc sine x over 2 and a constant. So because I'm multiplying by 1/2 and dividing by 1/2, those won't be there. And I can have a final integral for you, negative root u plus 2 arc sine x over 2 and a constant. So that's a pretty good example to show you some of the techniques we've learned so far over the unit, and seeing that you can apply them all and not just get your head fixed on one technique. So let's try doing some more here. This time we're still looking for the same values in the pattern. Once you've spotted that it's inverse trig, you're trying to find a value for u equals and a equals. So I've given you the hints here to get started while we're practicing. Usually the giveaway here, if I look at this piece, what would I have to square? Well, that's 3x squared. That's how I know I need to pick u as 3x. So it's not going to be set up for you and given to you like this normally, but while we're practicing, that's the way we can get started. So if that's the value I have for u equals 3x, then remember we also, before we're going to make any changes to this, we'd also have to go du equals 3dx. And the reason we didn't bother up here on these other ones is because du is just dx. So we don't need to make a change of variables here. There's no difference. The dx and du are the same, so we could just continue the way we were. But that's not the case anymore because it's 3 times what dx was. The value of a here is going to end up being root 2. And if you think about our choices, this one's going to end up pairing up with the arctangent. So there's our arctangent graph there. So in this case, what I'm going to do before I find my answer is I'm just going to plug in what I have so far. So far, I need a 3dx to be able to change this, which means I need a 1/3 in the front. So now my integral is in terms of u, and I have 2 plus u squared. And this one is ready to change it into an arctan. So this will be 1/3, and if you look at the pattern here, the first thing I need is 1 over a, so it'll be 1 over root 2, and arctangent of u over root 2 plus a constant. And in our situation, u is equal to 3x. So our final answer here is going to look a little bit more like this. It's going to be 1 over 3 root 2 times the arctangent of 3x over root 2 plus a constant. Now remember, when you see these answers in your textbook and whatnot, chances are you're going to have rationalized the denominators here. So you wouldn't see those answers. You would end up multiplying by root 2 over root 2. It's the same value, but if I rationalize it, this is going to become root 2 over 6 and arctangent of, let's see here, 3 root 2x over 2. So it may or may not appear that way, but don't assume that you got the question wrong just because you ended up with the square roots on the bottom. It may mean that you just need to rationalize your answer to see the same one that our textbook uses. Okay. Okay, so in the next example, again, we've got to recognize this as inverse trig. We go through our list of techniques, and we know there's no pattern here. We don't see something that I'm going to be able to use as a function in its derivative. And then I go to my last resort, which are these inverse trigs, and I can see here it's going to be the arcsecant. So to use the arcsecant then is my antiderivative, matching up the pattern, in this case u equals to 2x. So I'm going to need to make my substitutions like we did before, and if I do that, that means I end up with du is 2 dx's. And when I make those replacements here, I'm going to need a 2 dx, so I'm going to need a half in front. Now the other thing is I'm going to make my replacement here. This is u squared. But I'm going to also have an x, so I'm going to need to replace that. So I'll show you what would happen. We would rewrite this integral. We'd have 1/2 the integral, and now I've got u x root u squared minus 9. So this is that problem I was talking about. Now I have an x in here as well as a u. So what I'm going to do is I'm going to just solve it like you would in one of our substitution questions, so I can substitute in the value of u instead of x. So this will be 1/2 the integral of du over u over 2 root u squared minus 9. And in this case, I'm multiplying by 1/2 there, and I'm also going to be dividing by 1/2 there. Or you could just consider multiplying the top and bottom by 2, but regardless, those will simplify. So now the integral I'm dealing with is du over u root u squared minus 9. And what I'm going to need to do now is match this up to the arc secant. So the value for a that I'm using, if I look at my problem here, a is the value 3. And u is the value 2x. So if I put this back in, I have 1 over 3, the value of a, arc secant, and the value of u is 2x's, and the value of a is 3, and I'll of course also have a constant there. Okay, so again, I just want to practice another one with you here, continue to use this idea of substitution. This is a tricky one with e's that tends to mess with students. If you look at this e2x, what you should remember when you see that is that's like e to the x squared using the exponent laws. But it's harder to recognize the square because there's that extra x there, right? So watch that when you do see your work, that you are looking for those squares where you find them, because otherwise we wouldn't have a technique here if you didn't recognize inverse trig in it. And of course, with u being e to the x, we're going to also have to make our adjustment here with du being e to the x dx. So if I was just to start this problem the way we normally do in substitution, we would say, well, I'm missing this e to the x, so somehow I have to have an e to the x dx to make this replacement. But the only way I can do that without changing this function is if I also have an e to the x on the bottom. Otherwise, I've got a completely different integral. So that must be the case now, that I have this e to the x on the bottom and an e to the x on top, so that I can substitute my value for du on top. So before we do too many things at once, I'm going to make that substitution. And now looking at my problem, I can also make my change for u. So du over e to the x root u squared minus 1. And you know, this is just, we're just working on this now, but some of you might be able to recognize what we're going to do. And u equals e to the x, so we want to get rid of this because there's an x in it. We can't have an integral with more than one variable in our course. So I'm going to replace this with u. And of course that was meant to happen because if you look at our choices here, this is the one we're going with again. And if that wouldn't have happened, it wouldn't work out so nicely that it's arc secant. So now that I have everything set up, the only thing left in my problem is to figure out what's the value of a. And it's just 1 in this case. So here, I'm now going to work this out with the arc secant. So it's just 1 over 1. We wouldn't need to write that, so we won't have that in our final answer, of course. Arc secant of e to the x divided by 1 and a constant. So the answer here is just going to be the arc secant of e to the x plus a constant. Now, whenever you get stuck, you know, and especially if this was multiple choice or something like that on your AP exam, you may also find it easier just to work with the derivative, right? You want to check your work? Well, all you need to do then is take this function and find its derivative. So if I wanted to walk you through that one, I'd end up with the derivative of arc secant e to the x is 1 over, you may want to think about it like this, let u equal e to the x, so then it's going to be derivative arc secant of u will be 1 over u root u squared minus 9. And I have to multiply this by the derivative of u. So in my answer, that's how I'm going to end up here with this u and this u are both equal to e to the x's. The derivative of u, if that's the case, then my derivative is going to be also e to the x. So that's going to be an e to the x as well. So this would be, when I'm finished, e to the x root e to the 2x minus 9. These would disappear, and I would end up with the original expression, so I know that this is in fact the correct answer. Okay, so the last thing we want to do is, since this is where we're sort of leaving our techniques in the unit, we want to be able to recognize which one is this. Is this actually inverse trig? Is this substitution? What technique is this? Maybe it's natural log. So what I'm going to have you do is take a look at these and see what you think you'd have to do in order to answer the question. So this first one is quite clearly just a straightforward application of the arc secant. So we just did 2 problems with arc secant. Hopefully it's still fresh in your mind, but this one lines up directly to the arc secant. So if you haven't had a chance to think about these, I encourage you to pause the video and think one at a time. The next one I'm going to do is here, and then here, and so on. I'm going to work horizontally. So pause the video before we do them and see what you think the technique is going to be. Okay, so for the second one, the technique we're going to use here is substitution. How do I recognize that? Well, I see a function, and I see part of its derivative. So what I'm going to have is let u equal x squared minus 1. du is 2x. So that means I'm going to replace a 2 here and a half there to balance my integral. So I'd have 1/2 the integral of du over root u. And I always like rewriting these as exponents because I find it easier to integrate. So I'll have 1/2, add 1, divide by the exponent. Means those are gone, which means my answer is going to be root u plus a constant. But remember, u is equal to x squared minus 1. So this is what I end up with for my final answer. Okay, so again, I really encourage you to think about what could we do for these next ones. What technique would you use? So unfortunately for us, we don't have a great technique on this next one. If I was to use my natural log or use substitution, I would need to find an x somewhere in this problem, because the derivative of this inside piece is going to be 2x. So at the very least, I've got to have an x so I can multiply by my constant. So that's not the case. We can't use substitution on it. Now be careful. It's definitely not the arc sine or arc cos, because it would have to be this way. So we can't use the inverse trig on this one. So as deceptively simple as it looks, this one would be a calculator problem. This is one that we'd be doing with numerical integration. Now just to be clear, you won't be asked on the AP exam to integrate something that can't be integrated with your techniques. This question would be different, right? It would say something like, what's the integral from 0 to 5? Or it would give you a value so you could substitute it in your calculator. But the point is that you recognize the technique here won't work. We need to go with the calculator and do this numerically. So we could do trapezoid rule, we could do left hand, right hand, we could just use the calculator's integration. But anyways, regardless, it is a calculator question. In the next one, well, first thing before we give up on this one and say that there is no technique is we should separate it and then try to decide what's the function and what could be its derivative. Now, these are the 2 things that I have, and there's definitely a relationship between those, right? The derivative for natural log is 1 over x, so this is going to be my function, and this is going to be my derivative. So now what I have to be able to do is figure out how on earth am I going to relate them together. And if I give you this hint, I'm sure you'll be able to figure out what technique it is. I've just rewritten my fraction, it's a little bit more explicit. Now you can see this is going to be a natural log question because the function's on the bottom and the derivative's on the top. So that means I would have started with the natural log of x. So for this next one here, what we're going to end up using is, again, before we think too hard, we should split it up and decide what we can do. And again, I see that there's a relationship here between that function and that function. That's the function, that's the derivative. So that tells me that I probably have a technique that I'm going to be able to use. Which one is it? Well, the two functions are multiplied in this case. They're not divided, so it's not going to be a natural log derivative. It's probably going to end up being a substitution. So let's try and see what happens. So let u equal the natural log of x. du is 1 over x dx. So then I now have an integral that looks like this. It's going to be the integral of u du, which is u squared over 2 plus a constant. And for us, u was the natural log of x. So that's what I end up with for my final answer. Okay, so the last one, there definitely is a antiderivative for it, but it's not one that you guys have been exposed to. This is a calculus BC topic. So we can again just say this is a calculator problem. If we were to come across it, we would do this numerically. But I will show you how to get this answer. So that's enough for us today on the lesson, but I'll show you, for those of you who are interested, how you integrate the natural log using a technique from calculus BC. So for the rest of you, safely end it here, but I'll go on for those of you who are interested to see the antiderivative for natural log. So first, I guess I should give you some background on the technique. And this one, basically, one of the rules we haven't talked about in integration is the product rule. The product rule is really easy to do for differentiation. For integration, it gets to be a little tougher. That's why it doesn't come up till calculus BC. So let's just take a look at what happens to jog your memory. So say I have two functions. One is u and one is v. So if I take their derivatives, then I'm going to end up with u prime v plus u v prime. So each one gets a turn being the derivative. Now, if I wanted to go ahead and go backwards to integrate this, then if I took the integral, I would end up with the integral of a derivative. So it's the integral of, integral of a derivative, which is just going to knock each other out. So I'd have uv. And the integral of this whole thing is the same thing as the integral of uv plus the integral of uv prime. So this is if we already knew the answer, then we wouldn't be needing this technique. So what we're going to do is we're going to use one of these. I'm going to say if I have the integral of uv prime, it's going to be the same as uv minus the integral of uv. Oops, sorry, that one should be the u prime v. Okay, so all I did in the equation there, not very well I guess, was just to move this to the other side. Okay. So when you look at this, the reason the technique is useful is because if you think about what you're doing, u prime, this becomes u, which is the antiderivative. So if it's easy to take the antiderivative, like a polynomial, then we would choose it as the value for u. And if you look at what happens to v, v becomes its derivative. We like to choose v as something that's easy to differentiate. So let's rewrite this in terms of our problem. we have the integral of natural log x dx. And you're probably thinking, well, how are you using product rule? There's only one function. Well, that's where the clever part comes in. Now I have two functions, 1 and natural log x. That then, if I think about it, which one should be u and which one should be v? So I know this is clearly not enough time for you to grasp this lesson, but u is supposed to be one that's easy to integrate. So we don't want to pick natural log x, that's what we're trying to find, but lucky for us, 1 is easy to integrate. So I'm going to pick 1 as u, and v should be something easy to differentiate, which, yes, we already know the derivative of natural log x, so that'll work for us. So if I split this into two pieces, that means u prime is 1 and v is natural log x. So u is x, and the derivative of v is 1 over x. So I'm just going to substitute them now into this part of my identity. So u is x, v is natural log x, and u is x, and the derivative of natural log x, which is 1 over x. So I get x natural log x minus 1 dx, which is x natural log x, and that antiderivative is not so bad anymore. It would just be x plus a constant. So this is the antiderivative for the natural log function, which again it's not too bad to find if you're a Calculus BC student, but certainly not something that you'll be doing in our course.